algorithm C. Doesn't matter. You sign with these algorithms, you start signing with it, you continue, you re-sign with it, and you stop signing with it. That's what you do with the over 50 minutes. There's no such concept of rollover.
Okay. Yeah, I thought like maybe it's another room. Maybe I don't know.
But whereas key rolling, you're rolling over a set of keys using the same algorithm. There's no defined out. Going from RSA, SHA-1, RSA, SHA-256, or anything else. None of them there's no defined rollover there in the protocol. Whereas in the protocol there is rules for migrating from one key to another key using the same algorithm. And you can do that incrementally.
Very well. Welcome back, everybody. We have now the lightning session. So without further ado, James will be presenting towards measuring content locality. The room is yours.
Okay, thank you very much. Thank you for still being here, everyone, those who are left. So yeah, I'll be talking about our work towards measuring content locality. Hopefully. Okay. Oh, there we go. Okay. So yeah, we'll start with the definition of what local traffic is in this context. Quite simply, it is traffic that moves from user to a website and it remains in the country of origin. And conversely, external traffic is traffic that I don't think this is okay. Is traffic that goes via an international network between user and endpoint. So now we've got our definitions out the way. We will look at CDN deployment, and we're aware that there is a lot of previous work looking at this. Our methodology is slightly different in that we use much more fine-grained measurements. And in terms of geolocation, which I'll talk about later, we are not proposing a new method of geolocation. Instead, we are just utilizing current methods in order to put together our database. So why are we looking at content locality? Well, we've got the 3 Ps of motivation: policy, performance, and persistence. In terms of policy, we can use content locality measurements to check how traffic currently conforms to standards, such as those that exist in South Africa and the EU. We can also use content locality measurements to shape future policy, such as what's being done towards the Internet Society's 50-50 vision. And in terms of performance, local traffic is faster simply because if traffic travels a shorter distance, it will take less time at the same speed. I don't know why I've specifically chosen live streaming here, but as well as that, it can also lead to a benefit for the user because transiting international links is expensive. And so if content remains local, it can be cheaper. It trickles down to the end users. In terms of availability, local traffic provides a greater resilience against faults. For example, earlier this year in West Africa, there was a cable fault that meant that multiple countries could not access local websites, and they couldn't do things like paying their utility bills, which clearly is a problem, especially when everything is local bar where the traffic is going. I should also point out that local content isn't necessarily always better. We are aware that it can be used to increase censorship and also manipulation. However, we're just focused on how much content is local, not why or what it means at a wider scale yet. So how does our methodology work? Well, we have a 4-step process. We take the list of the top 1,000 domains per country. We then remove any censored websites. We determine where the website is hosted. And finally, we geolocate either the content provider or the domain itself. And the reason that step 2 is important here is because in step 4, we use residential proxies. And for those who don't know, residential proxies use devices in the country we're testing. And we don't want the people who run those devices to be sending a lot of traffic to censored websites just in case that gets them into trouble. So I'm just going to dig into the methodology a bit more. Steps 1 and 2 are quite straightforward. We just pull from online databases, and I'll talk about step 3 and 4 in a bit more detail. So to determine where our websites are hosted, we initially do a whois and CNAME lookup. We try and parse out any CDNs that we find in there. And if there's a tie, we can then do a tie break lookup of the headers. And again, we then just do a matching process. And if there are no matches, we'll take the whois first. So it's a top-down approach. And I should say that generally there is not a tie, and the whois and CNAME agree with each other. Now, to geolocate the domains, for those without a CDN, it's very straightforward. We take the domain, we put it through, we do 3 DNS lookups to get an IP address. We then put that IP address through 3 geolocation databases to get a locality, which we then add to our results. For geolocating CDNs, it's a bit more involved. So we take a CDN and an ASN in the country, and we put that into a residential proxy with a search string. We then extract the headers and the body. We put it through a regex to extract geo hints, which we then convert into locality and then results. And I'll just give a quick example. So let's say we're looking at Bunny CDN for AS200 in the Netherlands. So we put in our CDN and ASN. We use a search string we've determined to access the Bunny CDN. We extract the headers in this case. We put it through our regex to extract geo hints. And then in this case, we put it through an airport code lookup in order to say that for AS200, Bunny CDN is local in the Netherlands. In order to combine our results, we would say that if there are 2 ASNs, each with a 50% market share, we would then put the domain count through the locality percentage. So in this case, we have 5 local domains from Bunny CDN, 1 local domain that's natively hosted, and we then say that the country has a 40% locality. There are some limitations to this method. To start with, we don't consider website complexity. So we are just doing a lookup on the domain itself. We don't consider embedded content yet. We're also limited by where the proxy probes are. There are not proxy probes everywhere, and the amount of probes we have does affect the validity of our results. And finally, we've got what we're calling the fog of cloud, which basically just means when we get to that content provider, and this is a bit due to the website complexity, we don't know whether all the content is loaded or whether it's all cached at the endpoint we reach or whether it's brought from elsewhere. Again, we don't know yet, but that is something we'll look at in future. So now on to a couple of results. So we have done locality for each region, and this is quite a broad graph here, but we've also been doing our measurements per country. And again, this is affected by where the probes are. However, we can look at the global locality per country, and currently we're running these measurements every week so that we can start building up a pattern between how content locality changes with, for example, global events that are going on. We can also look at which CDNs are the most local, and this is just something else we can look at with our results. We can also check where websites are hosted, as well as which CDNs are most popular, which in this case, Cloudflare was well above the rest. And then something we're starting to look at is categorization. So this was just a random sample of 100 websites from the USA's top 1,000, which is why it doesn't include streamers and things like that. And this is still early work. We will hopefully build the results out a bit more from here. So in future, we are going to look at recursive searching, and this should hopefully address the website complexity issue. We're also going to include traceroute and latency measurements in order to hopefully dodge some of that fog of cloud stuff I mentioned earlier. So once we get to our endpoints, we can see whether it's likely that our data is loaded from the endpoint we reach or from further away. We will also start looking at the reasons for locality, which is arguably more interesting, but without the results, we can't start explaining why we think they might be that way. We're going to include greater visualization and finally increase our categorization that we've done. So just a quick summary. Local traffic is often beneficial. We are conducting global locality measurements and we're conducting them weekly, and we're still expanding the methodology. So yes, feel free to check out our paper or learn a bit more about the Internet Society 50/50 vision. And thank you for listening. I'll now take any questions.
Thank you very much. I can see David in the queue. Please go ahead.
Just a quick question about the definition. How do non-terrestrial networks play into your definition of locality?
That's a great question. They don't currently. So that is again future work, but yeah, good point. Thank you.
And if there are no other questions, let's thank the speaker. Thank you very much. And the next speaker is Nirmala Shenoy. Are you there? Hello, Nirmala. Is anyone from this paper present in Miteco? All right. Okay. Can you share your video? There should be some buttons at the bottom of the screen with a video and an audio.
Oh, okay.
Okay, there you are. Okay, Nirmala, the room is yours. Nirmala will be presenting investigating data center network protocols.
Okay. Hello, good evening, everybody. Sorry, I was just stuck with, I didn't know how to start the audio here. I have just a few slides here. Is it full screen, Ignacio, or do I have to do something?
Have you transferred the... Yes, you should be able to control the slides from your side.
Okay. So Peter Willis is my PhD student, and he has been working with me on data center network protocols. So it's more like a research project. So what I'm going to be presenting today is how we use the Fabric test bed to actually test data center network protocols. And we were primarily focusing on the more popular protocols that are used in folded clause topology. Working along with us is Yin Pan and Bill Stackpole from the Department of Security in our same college. Okay, so why are we interested in investigating data center networks and data center network protocols is because, this has been my research project for the last 3-4 years. So we noticed that, and even in some of the talks earlier today, there was this talk about with the advent of AI, data center networks are going to grow in demand and in size. And even now, believe it or not, there are so many data centers that are submerged in the ocean to cut down on their cooling costs and things like that. Now, while on one side we are trying to reduce the energy consumption, cooling costs, etc. On the other side, we notice that the demands and the complexity on the data center networks keeps increasing. And with the advent of AI, it is still going to get worse. Okay. So, and if we look at all the data center network protocols, I'm not looking at the server part of it, just if we look at the protocol side, you'll see that there are so many protocols which have been investigated and variations of these protocols have been used. But most of these protocols are just off the shelf protocols. So we wanted to see, can we investigate something that is just not based on protocols which are currently existing out there. And that can address major concerns which are faced in our networks today: energy and carbon footprint concerns, security concerns, the configuration needs. And we all know how human error crops into the configurations when you have to set up huge networks, which also happens with data center networks that are operating with BGP currently. So again, like I said, you will see that there are uh, quite a lot of new architectures and topologies that have been investigated. But when you look at the protocols that are being used in these architectures and topologies, they are variations of current routing protocols like BGP, OSPF, and so on. Okay, I'm looking only from a routed perspective. So when we started investigating these protocols for data center network, we said, okay, can we come up with a simpler protocol and so on? So we decided to go with a candidate topology, the most popular topology that's used in data center networks, which is the folded clause topology. And the more popular routing protocols that are used in these folded clause topologies, which is BGP. I don't know, are you able to see my cursor?
No.
No, you're not. So how do I point a cursor on the screen? Can I or can I not?
I don't think you can, I'm afraid.
Okay. So if I'll just try to explain with whatever is there on the screen. So you see two colorful blocks there. On the left side is the current DCN router protocol stack that's being used in folded clause topologies, and they use BGP for routing. Okay, that's the most popular protocol that's being deployed in folded clause topologies, and they have ECMP. They use ECMP because folded clause topologies has got multiple paths, and you want to equally load these different paths. So BGP along with ECMP is used. And to run BGP, you need TCP because BGP has to run on TCP. And then to speed up the failure recovery, which is very, very important in data center networks because we should have very low downtimes, they use BFD, which is bidirectional forwarding detection. And then BFD requires UDP. And then all these protocols are running on Internet Protocol. And what we came up with is a simple single protocol, which we call as MRMTP. It's the multi-route mesh tree protocol. Okay. And this protocol performs all the essential functions that for which purpose we sort of retrofitted all these protocols to do. It does routing, it does load balancing, it has a very quick failure recovery, it does not need TCP, it does not need UDP, and we sort of did away with Internet Protocol because we wanted to have a non-IP solution which is not constrained by all the requirements that you need to run any protocol on the Internet Protocol, like BGP, OSPF. They are all designed to work on the Internet Protocol. We wanted to be free of that, and that's where we came up with this. And this paper is more about investigating this protocol. And of course, we are trying to use a fabric testbed, which is what you see here. And I noticed that one presenter earlier also used this fabric testbed. It is a widely deployed testbed in the US. It's got you can reserve resources, set up topology. So that simple folded clause topology that you see on the right side, That is the one we deployed on the test bed, the Fabric test bed. And we coded our protocol, the multi-root mesh tree protocol. We coded it in C. Due to the limited time, I'm not going to go into the details of how this protocol works, but you can have a look at these papers which were published in SIGCOMM FIRA 2022 and 2023. The 2023 paper is better because it's got more details. 22 was more concepts. And we also made a presentation in NANOG 91. I actually provided a YouTube link. Nanog 91 recorded the whole presentation and it is available in YouTube. So I think because they converted this into a PDF, some of my figures are sort of overlapping and I'm sure you lost the link to it. But you can look up Nanog 91 YouTube presentations and you should be able to pull out this presentation, which gives you all the details on how this very simple protocol is able to set up routes and do the forwarding. To cut short everything, all that we do is, all these are the TORs, L11, L12, L21, L22, they are the TORs. And from the TORs as root, we construct mesh trees that reach all the top tier spines without forming any loops. Okay, so one of the major challenges we face in our routing protocols is loop avoidance. And this is actually a very simple scheme. And that's where I would request you to have a look at the presentation that sets up all these routes. It's got animations on how the route setup is done. Okay. Now, and my PhD student, Peter Willis, he's great with setting up all these automated tools in Fabric. So there's a whole bundle of tools. Again, I have given you a GitHub link here where you can set up topologies to test BGP. We downloaded BGP from the FRR routing, all the protocols required for comparison. We downloaded it from the FRR routing site, and we used his very nice automation script that you see here that can be used on the Fabric test, but you can use it for any other purpose also. You can tailor make it. He has built it in such a way. And so the test cases that I'm going to be presenting to you are, we do fail at all those test points, TC1, TC2, TC3, TC4, and we send traffic from the compute node 11 to a compute node which is sitting in pod 4. And we tried, the only result that I presented in the paper, because it was a 2-page paper, was the packet loss. So for all these 4 different failure points, how much packet loss do you face? And that is what you see here. You can see we are comparing it for a 2-pod topology and a 4-pod topology. And if I do not, the y-axis is a log scale. That is because the loss of packets if I use just BGP, ECMP was pretty high for some of the test cases. So the blue one is test case 1, orange is test case 2, and so on. So you will notice that we were losing more than 4,000 packets. I was just sending a stream of packets between those servers, and that is a loss of packet. And the last one, to the extreme right, we introduced BFD into BGP, and you notice how much it cuts down on the packet loss. Fabric is a very good tool to test it out. And you can just imagine if I scaled this network to multiple pods, what will be the benefits of looking into simple protocols like MRMTP. And like I said, you can test these protocols using the Fabric testbed. Looks like I'm running out of time, so I'm just going to end it with this. And the takeaway for me is, and this is predominantly my research area, do we need routing protocols at all in networks today? You have beautifully structured networks, very definitive architectures. We don't throw routers and switches around. And using those structures, you can auto-assign addresses on auto-established paths that can do all the routing for you. It'll cut down on your configuration needs, errors, auto address assignment. It's a non-IP based solution, but it's backward compatible with IPv4, IPv6. It can be used with limited domains which are currently struggling with the IP addresses. Any special addressing you can use with these types of protocols. This is just a beginning. They can be extended for intra-AS routing as well. Okay, so this is one solution that we are looking at. And coming back, if a router, I replace 5-6 protocols with a simple protocol, look at the cut down on the energy costs, equipment costs, maintenance costs. That's all a great study to be done. No BGP, no TCP, no IP. All the security threats that we faced against these protocols can be avoided. That is one of the studies which we are currently doing. So I think I'm going to stop it here because I seem to have run out of time. I have added some more slides from my other work. Like I said, I was not able to add much on the...
Thank you very much, but there is only 1 minute left, so probably better to leave for the questions. I see Thomas and Lars in the queue.
Okay.
Yeah, hello. Question, to my understanding, many data centers run SDN. Have you evaluated how this interacts with SDN controllers and networks?
I don't think there is a need for SDN in this case because, this is a very simple protocol. It is able to establish path. I don't need any sort of a central controller to control all those path establishments or decide on the paths to be used. And adding SDN, adds another level of complexity. And there have been severe security issues against SDN-based DCN topologies that have used SDNs. So I'm trying to keep away from that. Any other extra features, if they need to be added, they can be added in this protocol because look at it like this. This protocol was designed and developed by us. You want any other feature to be included, we will add it.
Hi, Lars Eckert. Very briefly, how do you do congestion control if you don't have a TCP layer? Because it doesn't look like your routing protocol does that.
TCP in the routers are not there for congestion control. They are there because BGP requires TCP.
So you're running TCP on top of your routing protocol then, end to end?
No. TCP is running still on the servers. This solution is only for the DCN routers.
All right, thank you very much. Let's thank the speaker. And we have our next speaker online, presenting Quick Pro, integrating deep reinforcement learning to defend against quick handshake flooding attacks. The floor is yours.
Hi, everyone. This is Vardar. I'm from Concordia University, Montreal, and I'm going to present Quick Pro, integrating deep reinforcement learning to defend against quick handshake flooding attacks. This works with my supervisor, my PhD supervisor, Carol Fang, as well. I'm going to cover introduction of Quick Pro, quick overview, previous research works, motivation, problem statements, Quick Pro framework details, planned implementation details, expected outcome and benefits, and finally conclusion and future works. Introduction of Quick Pro. It utilizes deep reinforcement learning with proximal policy optimization algorithm for dynamic security optimization against handshake flooding attacks. Quick Pro employs real-time rate limiting, connection prioritization, and traffic shaping. And it also implements the isolation forest and for the anomaly detection and support vector machine for the pattern recognition. And Quick Pro features a feedback loop for ongoing improvements of security policies. So Quick Pro is for Quick Protocol. So Quick is a UDP-based multiplex and secure transport protocol. It provides flow control systems for structured and efficient communication. It gives low latency connection establishment, and Quick supports network path migration and also offer zero RTT and connection migration feature. And finally, Quick enhances security with measures for confidentiality, integrity, and availability. Our previous works, In 2022, we published a survey on the security issues of Quick, where we figured out multiple security issues. And in 2023, we published our specific Quick handshake related issues titled as an empirical approach to evaluate the resilience of Quick protocol against handshake flood attacks. And on the same year, we come up with a detection mechanism called Quick Shield. It is a statistical mechanism, a rapid detection mechanism against quick flooding attacks. And earlier this year, we published a machine learning based approach that is called Quick Wand, a machine learning optimization based hybrid defense approach against quick flooding attacks, where we use Bayesian optimization for that. And now we have come up with Quick Pro, integrating deep reinforcement learning to defend against quick handshake flooding attacks. Motivation of our works: quick handshake process is vulnerable to flooding attacks with a 4.6 times CPU amplification factor. Traditional TCP SYN flooding detection mechanisms are ineffective due to Quick's distinct handshake design. Quick Shield, a prior defense solution, has a higher false positive rate and potentially blocking the legitimate traffic. Quick Wand lacks adaptability to rapidly evolving the network condition and sophisticated attacks. Problem statements. Malicious attackers target Quick's handshake mechanism, leading to network disruption and resource exhaustion. And the current defenses for the quick handshake flooding attacks like Quick Shield have high false positive rates and diminishes detection accuracy in the dynamic environments, while Quick Wand lacks adaptability. Quick Pro framework. Quick Pro utilizes deep reinforcement learning with PPO algorithm to dynamically optimize security measures against handshake flooding attack. Functionality: it detects and mitigates quick flooding attacks by continuously monitoring network traffic and adjusting defense mechanism in real time. Dynamic optimization: Quick Pro leverages machine learning to adapt detection and mitigation strategies based on current network condition and emerging threats. Improved accuracy: it reduces false positives and increased detection accuracy compared to previous methods such as Quick Shield and Quick Wand. In quick simplified handshaking, there is an issue that is unverified response issue in the first round trip. And quick handshake flooding attacks can be happen in 3 scenarios. One is version negotiation without address validation and with address validation. We proved it in our previous paper called Quick Wand. Core components of Quick Pro is deep reinforcement learning agents, network traffic monitoring module, and adaptive defense mechanisms. Deep reinforcement learning agents use proximal policy optimization to learning and optimizing security policies based on environmental feedback. And neural networks with convolutional neural networks for the feature extraction and followed by fully connected layers for decision making. Network traffic monitoring module continuously monitors incoming traffic to Quick servers and uses machine learning algorithms like isolated forest for anomaly detection and support vector machine for the pattern recognition. Adaptive defense mechanism employs dynamic rate limiting, connection prioritization, and traffic shaping techniques, and adjust in real time based on the feedback from deep reinforcement learning agents and the traffic monitoring module. Planned implementation details of Quick Pro involves integrating with existing quick implementations like AI Quick, Quickly for seamless operation, and deep reinforcement learning setup with the algorithm and neural nets uses proximal policy optimization for the algorithm and neural nets for CNN for the feature extraction and followed by fully connected layers and decision making. And in the case of network traffic monitoring, uses continuous monitoring by utilizing isolation forest for anomaly detection and SVM for the traffic for the pattern recognition. Expected outcomes and benefits: high Quick Pro has high detection accuracy, reduced false positives, dynamic adaptation, and enhanced resilience. Conclusion and future works: Quick Pro has effective detection and mitigation techniques, and it has low false positive rates, and with enhance the resilience. And in our future works, we will focus on the multiple quick libraries implementation to see the proper results on the variation. Now, currently we're using the DARPA dataset as an attack dataset by manipulating regarding to our projects. But in future, we will test against the diverse attacks and as well as the developing a comprehensive quick attack dataset. Thank you, everyone.
Thank you very much. Do we have questions?
Hello. So I have one question. So did you try testing this on real world quick traffic to see how Quick Pro is performing?
In real world, we didn't do it yet. It is our ongoing projects currently. So what we are doing now, we take as a we collect the quick data and from using Wireshark, and as a attack data, we collect the DARPA dataset from the TCP DDoS dataset. So we modified it as scene for Silo and act for CNAC for the server hello, and we see the only using AI quick now, but we have a plan to use it in multiple implementation like quick libraries, and after that in the real scenario as well. Thank you.
Lars Eckert, a quick question. Have you validated that you're using less CPU time for the training and running of your model than you would use for absorbing the flood?
Thank you for your question. We validated in our previous two methods. One is called Quick Shield and Quick Wand. One is statistical and one is machine learning based. But this one, we just, I mean, based on the previous results, we are still working on that.
Right, very well. Let's thank the speaker.
Thank you.
Okay. No, let's see stream from her side. Hello, Tanesh. Just 1 second. Your slides should be coming up.
Okay. Am I audible?
Yes, we can hear you. Somehow your slides are not coming through. Now.
Yep,
Here
yep.
they are.
I'm sharing.
All right. So next we have Danesh Sainali presenting BBR v3 in the public internet. A boon or a bane? The room is yours.
Okay. Hello, everyone. I am Danesh, and today I am presenting on behalf of my colleagues and collaborators from Max Planck Institute for Informatics and FU Amsterdam. This is a work about BBR v3 in public internet. Okay, just to refresh your memory, I know everyone is familiar with BBR. The first version of the BBR was introduced in 2016, and it was a big paradigm shift in that date, because all of the CCAs were just relying on delay or loss to detect the congestion, but they decided to use estimation of bandwidth or delay and also probe and drain to avoid filling the queues. And it was in the main line of the Linux kernel from version 4.9. So BBR was really important because in 2019, just 3 years after the introduction of the first version, a study in here that I'm showing the snapshot of it shows that 22% of the Alexa's top 20K websites were using BBR, and by their estimation, it's more than 40% of the internet traffic that date. And early after the introduction of the BBR first version, Jeff Histon evaluated it because of this huge migration of the traffic to the BBR. And as you see in this blog post in the RIPE Labs, that he's showing the average throughput over time of a cubic flow that is competing with the BBR flow. As you see, the cubic flow at the beginning, the red one is starting, and the BBR flow is joining to it after 20 seconds. And as soon as the BBR flow is joining cubic flow, doesn't have any chance to grab any of the bandwidth. Also, another study in 2019 shows that even a single BBR version 1 flow can grab most of the bandwidth or 50% of the bandwidth while it is competing with 16 independent cubic flows in the same bottleneck. So the Google team redesigned redesigned and implemented a new version of the BBR. BBR version 2 was introduced in 2019, which the big change was a reaction to loss and also ACM, and also some adjustment to parameters to ensure fairness to the loss-based protocols. So again, researchers studied this new version, and as you see, the second version of the BBR is totally fair to the cubic flows. Until last year that the third version of the BBR was introduced, and it was a minor evolution of BBR version 2, which was supposed to fix bandwidth convergence with or without loss and or ACM marks, and also some performance tuning for better performance when it is competing with the loss-based protocols. And the promises was that better coexistence with the cubic or Reno, also lower retransmission rate and reduced latency for different buffer configuration. Similar to the previous works, we also decided to see how these promises work in the internet. And we set up a very simple test with a dumbbell topology where we have a bottleneck in the middle. It's 100 megabits per second bottleneck. And we used off-the-shelf Linux tools to configure our queues, buffer sizes, and also our delays. We did a comprehensive evaluation. For example, I'm just giving some examples in here. Intra-CCA fairness, where two BBR flows were competing with each other, or RTT fairness, where the RTT of these two BBR flows were different, and also coexistence with loss-based protocols, which was the classic problem we saw in the previous slides. And some real-world network traffics that not only we have mice, elephant flows, long-lived flows like that are called elephant, also we have some short flows that are called mice. This work has been published and presented in the PAM 2024. If you want to see more details about it, please read the paper. But for in the interest of time today, I'm just focusing on coexistence with the loss-based CCAs. So at the beginning, we started to reproduce the previous results, one BBR version 1 competing with one BBR, one cubic flow. And as you see, the flows are starting at the same time. And this plot, I'm showing the throughput over time. And as we were expecting from the previous work, BBR V1 is dominating cubic. But it was really surprising for us that we saw that BBR V3 has a similar behavior, or sometimes even worse than the first version of it. Also, in the introduction, I said that a single BBR version 1 can grab more than 50% of the bandwidth when competing with 16 cubic flows. So we decided to have a similar experiment where we have 1 to 5 cubic flows I'm showing in the x-axis that are competing to 1 to 5 BBR flows. In each cell of this, I'm showing JFI at the top, Jane's Fairness Index at the top, which is the number and also the big number and also the color of the cell. And at the bottom on the right side, I'm showing total cubic flows share, and at the left, total BBR flows share. For example, in this specific cell where one BBR flow is competing with 5 cubic flows, we see that those 5 cubic flows only have 20% of the link, while the single BBR flows grab more than about 80% of it. If we repeat this experiment with BBR version 2, we see that the fairness is much better, and also the bandwidth share of the cubic and BBR are reasonable. We repeated this with BBR version 3. It's somewhere in between, but it's leaning towards the BBR version 1. It's the fairness is lower than the BBR version 2, and also you see that cubic flow, 5 cubic flows only have 40% of the link, while the single BBR flow has 60% of the link. If you look at the top left extreme case of this experiment, you will say that okay, the fairness is good in that area. But if you look at the numbers in the bottom, you will see that cubic flows almost are dead when they are competing with several BBR flows. So BBR flows are fairly sharing the link among themselves, but they are not letting the cubic flow to live. For BBRv2, the case was a bit better. So we can overall say BBRv3 shows unfairness towards multiple cubic flows as seen with the BBRv1. Another big change from the version 2 of the BBR was ECN, and also ECN is going to be deployed more in the internet. So we decided to take a look at how it is performing while the ECN is on or off. Just a quick recap again. For ECN, when two or several flows of TCP are competing with each other and the bottleneck router supports ECN, after the queue build up after certain threshold, they are marking the packets with a congestion encounter. These packets go to receiver. Receiver reflects them back to the sender, and sender is receiver to react to them. Let's see how BBR was designed in this. As we know from previous presentation by the Google team, that the BBR design was DCTCP inspired ECN. So we took a similar configuration to their configuration, where we just scaled the marking threshold. We have just 100 megabits per second in here, and the whole RTT of the system was 100 milliseconds. Here I'm showing the result of BBRv3 versus cubic, because in this case the queuing mechanism is different. In the previous slides that I showed, queuing mechanism was FIFO, but in this case it's Codel. So still BBRv3 is not fair to the cubic, and by enabling the ECN, the result is even worse than the previous one. So we repeated the experiment where we had 1 to 5 cubic versus 1 to 5 BBR flows. And as you see in the right corner, in the right bottom corner, cubic flows only have 3% of the link. By enabling the ECN, even this percentage decreases to 0.5%. Even in the case at the top left as well, we see that the share of the cubic is not really that much, and the BBR flows probably are fair to each other, definitely are fair to each other, because the fairness number is high. So just in conclusion, we did an evaluation of coexistence of BBR with cubic, and we saw that without ECN, this coexistence was not that well. Even enabling ECN didn't help the case to improve the performance of the fairness of the BBR to the loss-based protocols. So just in conclusion, we believe that Google has done a great job implementing a new CCA that was a big paradigm shift compared to previous congestion control algorithms, and evaluation of a congestion control algorithm is definitely a challenging task, and we believe that us as a networking community maybe should consensus on some kind of guidelines how to evaluate CCAs to before deployment in the internet. So if you want to read more about our paper, scan this URL, scan this QR code and visit our website. Thank you.
Thank you, Dinesh. Are there questions? I see Michael on the microphone, approaching to the microphone. Please go ahead.
Hello, this is not a question, just a small comment, because you kept saying this is a big paradigm shift. I think it's good for the community to be aware that there have been some TCPs that did these kinds of things before. It's not that new. I mean, Westwood has always looked at the accurate and used that as a guidance to understand the capacity.
Okay,
Just saying that,
thanks.
it's just a side comment.
Thanks, thank you.
And I see Navas. Sorry, I struggled with your name.
Just a comment about the ECN comparison. I don't think it actually makes sense to compare it because the BBR-V2 and V3 is ECN is TCP, DC-TCP inspired and DC-TCP, and comparing a DC-TCP inspired ECN response to a classic ECN response will result in results like this. But this is, I wouldn't say this is a flaw in the V3. You should compare it to Prague or DC-TCP rather than Cubic.
Yeah, I see your point, but in the documents that we saw in the Google's reports, we didn't see that anywhere they say this is just for the data center. So we thought maybe it's gonna be deployed in the internet as well. That's why we did this.
Okay.
Thank you.
And Michael is back.
Me again, speaking about ECN, the key thing is this ECT0 or is it ECT1? Do you know what it used?
To be honest, I don't recall.
So if it's ECT1, right, then this is for L4S, and it doesn't make sense to compare it in the way you've done. If it's ECT0, then it would make sense to compare it like you've done, I think. So.
Okay, I will look that up, definitely. Thank you.
And Reese is next.
Hi, Reese Enghart. If I understood you correctly, you said you wish there were guidelines for evaluating congestion controllers before they get deployed on the internet. Well, I have good news for you. We have a draft in the congestion control working group, 50 Shows Your Biz,
Yep.
and I invite you to take a look at it and come back with more evaluation with BBR3.
Of course, I'm aware of that, and we are looking for any collaborations or data sets or whatever the community can help us to improve the evaluations. Thank you.
That's great, thanks.
Well, let's thank the speaker. And is the next presenter in the room? So you're going to present from your computer? Yeah. Okay. Put a timer.
Sorry?
I will put a timer so you can see the time.
Yeah,
sure, left and it include the Q&A so you're aware. Okay.
Sure. Hi, I'm Punal Ismail. Sorry.
Go ahead.
Yeah. Hi, I'm Punal Ismail Khan. I'm a PhD student from UC Santa Barbara. Today, I'll be presenting my paper that is about the tool we are working called NetMosaic. This is a joint work with collaborators from ETH Zurich, Nixon, and my colleagues from UC Santa Barbara. So ML models for networks. So if you look into this space, there are at least 1,000 research papers, multiple product and startups have been created, and overall billions of dollars have been invested. So given these investments, our expectations are easy to develop ML models for any given problem and target environment, and abundance of production-ready ML models ready for high-stake decision making. But in reality, few, if any, of these models have ever been deployed in production settings. So for example, these are some of the models in the literature. Why can't we deploy these in production? So the problem is they suffer from generalizability issues like shortcut learning, out of distribution samples, and spurious correlation. And hence, most of these ML models fail to generalize, meaning they don't perform well on new or unseen data, and so are not ready for production deployment. So how do we develop generalizable ML models for network? So this is a standard ML pipeline. Let's say we use CI/CD-IDS data to detect malicious traffic. Is this the right data? Next, we get unusually high F1 score. Is the model underspecified? For example, model might be learning a shortcut instead of truly understanding the traffic. So how do we collect better data at scale? Answering these questions is critical for developing generalizable ML artifacts for networking. So recently there has been progress in this. For example, PNOT presented here last year can transform your production network for data collection. Trusty presented in CCS 22 can take in any trained model and gives you an easy to interpret decision tree and a trust report that a domain expert can then use to understand model specification issues like shortcut learning. Next, you can use a tool called NetUnicorn to endogenously curate new data sets which don't have these under specification issues like shortcut learning. So, but and you can repeat this cycle continuously, eventually getting rid of data related problems. But does NetUnicorn truly solve the problem of collecting the right data? So uh, a bit of review on NetUnicorn. So before NetUnicorn, you had a learning problem and network environment. You had to write separate data collection pipelines for each learning problem and a network environment. What NetUnicorn did was provide this thin waste where it decouples the data collection intents for different learning problems from the deployment mechanism. Hence, this abstraction simplifies collecting data for any learning problem and target environment. But NetUnicorn has this limitation. So to curate realistic traffic, you have to mimic real world, you have to mimic application diversity of real world data. But writing that application logic is a manual effort, and hence it is hard to scale, right? And the application logic that you write might break over time as well because of updates in application that affect your code. So hence you will have to have more manual effort in this. So how do you scale data collection for new applications? So for this, our idea is to use already available resources in the form of publicly available GitHub repos that can capture diverse application logic. And prior work has also shown that there are around 70K GitHub repos which contain containerized application that generate diverse network traffic and can easily be deployed using a Docker Compose file. We refer to this as big code. So can big code address NetUnicorn's limitation? So this is our earlier figure of NetUnicorn. This is where our system NetMosaic comes into picture. So it uses big code application diversity and subsume platforms like NetUnicorn to deploy it in physical and virtual networks. Hence, it gives us the ability to curate more data and hence argue about argue about the model's inability to generalize. But does it enable curating a better data set? So for this, we consider a learning problem of traffic classification. Here we identified services based on encrypted packets in a flow. Our data source was the 16K GitHub repos, and we labeled them using IANA port numbers, port and service mappings. And we curated this data where we got, and this data had 1.7 million flows and 54 million packets. And apart from that, we had 264 unique services that shows the application diversity that this data had. Our top services include HTTPS, Redis, PostgreSQL, Forward MongoDB, and MySQL. I think it stopped working. Just stopped working. Okay, yeah. So other than the application diversity, along with this application diversity, NetMosaic was able to curate far bigger data sets than some of the other available data sets in the community that is used for traffic classification. So NetMosaic is able to curate this better data set, which is more diverse and realistic. But does it enable developing generalizable models? For this, we deployed, collected some data under different network conditions introduced in a virtual network. We did this by deploying services in a virtual network using Docker Compose file present in 256 GitHub repos. And so we collected two source datasets, dataset A and dataset B. In dataset A, we didn't place any limit on the network condition, whereas in dataset B, we placed limits between links in different containers in a Docker Compose file to introduce some congestion, a low congestion. And after that, we curated a target data set, which is an unlabeled data set used for assessing the model's generalizability. Here, we introduced high congestion, and by congestion, I mean high packet loss, high latency, lower bandwidth. And finally, we trained random forest decision tree logistic regression in MLP using dataset A, which is the default setting, dataset B, which is the low congestion setting, right? And after this, we tested their performance, the performance of, one more thing. So the models trained with dataset A, we call them model A, and the models trained with dataset B, we call them model B. So here we tested the performance in the form of F1 score for model A and model B for source dataset and target dataset. So for model A, the source dataset on which source dataset is the dataset environment on which we trained model A. So when we tested it in dataset from the same environment, we got decent performance with random forest and decision trees. Model B also exhibits similar performance when tested on source dataset. But when we tested it on target dataset, which was the dataset with high congestion, we see that there's a great performance drop, hence highlighting issues with generalizability. But when we tested model B on the target dataset, we see performance drop, but not that much as it was for model A, hence highlighting some generalizability. So this makes us think that using training data collected under more realistic network conditions could improve models' generalizability. So these are the summary and the next steps. So we learned that our system simplifies collecting data for different applications under different network conditions by leveraging big code and platforms like NetUnicorn. Next, the prototype implementation exists, and it demonstrates the ability to create better data sets that we can use to study and like improve models generalizability. What's next? So for this, as this is still an ongoing effort, we want to develop some closed loop workflows where we can study like which network conditions are affect the data quality the most, and also leverage model explainability tools like Trusty to shed light on which aspects of network conditions and application logic affects the model models which affects the model generalizability the most, and also for which kind of learning problems. And lastly, we also want to scale data collection for more repos and improve data quality by addressing class imbalance issues and filter noisy samples. So, thank you. And I can answer any questions or if you have any comments.
Thank you very much. Questions, comments? Don't see any comments or questions, so let's thank the speaker. Thank you very much.
Thank you.
And last but not least, we have Jerry, who is going to present the large language models dream of sockets.
All right. Hello, everybody. Thanks for staying until the late evening. So I will talk about large language models and what they might have to do with protocols. And so what is that about? So there's obviously been lots of excitement about large language models recently, but mostly in terms of like chatbots and programming assistants and so on. And for me, as a protocol engineer or network engineer, that doesn't do that much. So that's not exciting, I think. So we started asking whether you could actually have some of these models speak, in quotation mark, these protocol languages natively. And it seems that that potentially should be possible given that there's multimodal generative AI tools available for other things. So why not protocols as well? Of course, this is not totally new. We have various kinds of things. You take yourself to the nearest chatbot and you can ask it to construct protocol messages to some degree of success at least. We've also had recently people publish work on building tailored models specifically for the digital world. We have had people look at use of large language models for the protocol work, for instance, looking at specifications and so on. So there's many related works. So what is our vision? Our vision is that you somehow acquire a set of training data that is in the form of packet traces, for instance. And then you feed this to an LLM system as training data, and then we make something interesting happen. And what is that interesting? That could be actually several things. It could be diagnostics, explaining what's going on. It could be test data generation. It could be simulation, or even quick prototyping. And our research approach has been try and understand if this is feasible and to what extent. Keeping an open mind, maybe it works, maybe it doesn't. What are the issues? There's also different ways of doing this, so we try to test those different techniques. This is early work, that's why this is a lightning paper, so we just basically started. We have some results, but not super much yet. But we already run into a number of challenges. The first challenge is that protocols usually have like these complex fields, length fields, checksums, encryption, and so on. And the LLMs, they're not very good at dealing with math, and maybe we shouldn't even ask them to do that sort of thing. And for some of these problems like encryption, you, in principle, shouldn't be able to do it. Also, protocols are not everything, even though we protocol designers like to think that's the most important thing in the world, but typically there's like configurations and other stuff in systems that affects the behavior. So if you try to understand the behavior, protocol is not enough. Also, we should be very, very worried about letting our large language models or AI systems send messages around the network or access resources. We really need to think about what the security implications of that are. Of course, hallucination is a problem. We had some discussion about that in the context of the keynote this morning. Yeah, you can't get to 100% correctness. What does that do for your use case? And then we have many efficiency problems. We do have some partial solutions in our work for this. For the complex fields, we've sort of combined traditional techniques like message parsers and constructors together with LLMs and sort of both do like their part. If the question is that like we are looking at protocols, but that's not enough, we can of course also look at the other aspects of systems, like look at what the configurations are, what the file system accesses are, and what's happening in other interfaces. For security and safety, an obvious answer is some kind of limitations or sandboxing, at least a partial answer, maybe not the final answer. Hallucination, that's a big problem. Some of the things that we discussed this morning can help, but also ultimately you need to think about what use cases are feasible given the possibility of hallucination. So typically where the human is ultimately involved, and then maybe that's a more reasonable case to use. And then for efficiency, I won't go into details of that, but you can have like, you can use the LLMs to do a task, or you can use the LLMs to generate code to do a task, and then the code runs faster than the LLM instead of sort of repeating the same thing a billion times, which might be slightly costly using these tools. Okay, so I have two example use cases. The first one is diagnostics. And the context here is that basically you would feed expected behavior or normal behavior as training traces to the LLM. And then you make a question and you feed a sort of suspect trace or problem trace, what's happening here. And then the LLM would output what happened, and it would, that output would be potentially useful for a human who's trying to understand what's going on. And having stared many TCP dumps in my life for a long time and not understanding what's going on, some tooling here would be super useful. Here's an example, a simple HTTP trace where the AI is explaining that the method name is wrong and hi is get in Finnish, and that doesn't really work in the protocol. So that's why you get an error. The AI got that. But that sort of anecdotal evidence, we also attempted to do a little bit more systematic approach where we created an artificial protocol, created a set of messages in that protocol of training data. We created examples of errors and examples of non-errors, and then tested the ability of the LLM to identify whether there are problems in these example traces. And we did this by having a human that will be the researcher trying to check what the results of the LLM are, if they are reasonable or not. And we also, because there's many ways of doing these techniques, whether you feed, for instance, direct binary input, or you feed the results of message parser and so on. We varied the techniques that we used, and then we were able to compare like how do the different techniques fare compared to each other. And I won't go into too many details of these results. There's a little bit more in the paper, even though it's short. But basically, the bottom line is that the chosen approach does affect. So, for instance, if you can use the message parser, then you get a little bit better results for various reasons. And also the other observation is that we can get to sort of reasonable, or in my opinion at least, reasonable level, sort of high 90% accuracy of identifying what the problems are. But more work is needed. So this was just for one example. We're continuing the work trying to understand this with more realistic protocols and bigger real world protocols. Another use case, simulation, and this is kind of like science fiction use case maybe. I'm not really sure if this is really feasible. One of the issues here is that because of these hallucination problems, you might not get to 100% accuracy. So is that a problem, or is that not a problem? Maybe that's not a problem for simulation. If you try to use this as a final product, that could be a problem, or likely is a problem. But it was kind of interesting to see that you can record the behavior of systems and have the LLMs learn that behavior. So one simple example where we did this, we recorded web service behavior, and a Apache server was installed. And then we look at what's happening on the network interface, and then we look at what's happening at the OS interface, basically using the strace tool. And this is training data. And based on this training data, then the LLM figures out that, if I get this GET request and with a file name, then I should open the file name using the open call. And if I get -1, then that should lead to 404 result, and with the relevant results. And if I don't get -1, I get actual data, then the data should go here in the response, and then the length of the data should goes to another place, and so on. So it was kind of a fun exercise. Yeah. So conclusions, we've had lots of fun trying to do this experimentation. We found this exciting in general. We think that the protocol and system behavior patterns are a good topic for LLMs. There are some use cases where this seems potentially useful, like the diagnostics. There's some other use cases where we don't know, or are doubtful, like the simulation or system implementation. We also realized that it's important to not just apply this LLM technology that I have one tool and I'm going to apply LLMs for everything. And if it doesn't work, then I wait for the next version of the LLM. That's not how to work in our opinion. Rather, it's better to understand like what are the different tools good for. Like you can use this tool for this task, and then this other tool for other tasks. So we chose to use the LLMs in this work to sort of understand the patterns of behavior rather than the detailed bit level tasks or bit level operations. Yeah, and plenty of research remains both on the diagnostics angle and the other angles. And that's it. Questions?
Thank you very much. Do we have questions? Then maybe a question from my side. I don't know if you have seen there is some work on foundational models for networking by Nick Fimster, Pete Gupta, come to mind. I'm sure a few others.
I'm not sure I've seen that specific work, but I've seen many other things. I can look it up.
Yeah, it goes in the same direction, and some of the problems they encounter, among others, at some point, like they realize that what they have is a multimodal LLM, because the protocols are not necessarily the same, talking the same thing, right? Like a large language model predicts the next token in a sequence, and every protocol might be having its own sequence. So
yeah, and that's actually, I mean, we've run into that as well, and that's often a feature because you have this situation where you have potentially multiple different things and in different sides of the box, and they're all different sequences. You need to understand that as well, and not just like the single behavior. And also, like at the very basic level, like you do diagnostics, it'd be really nice to get the explanation in English, right? That's why it's useful to have the LLM be able to speak English to the user that, hey, your method name is wrong.
And I see a question from Christopher.
Hi, Christopher Nacio. Did you compare different like LLM engines, or so like, do you have any insight on that? Because you're just fine tuning them, right?
Well, our research team is actually having sort of multiple approaches. We're doing fine tuning. We're doing like building the actual new models, foundational models. This particular exercise that I'm presenting now is basically in context few-shot learning. But we have compared the different models, and the work that we did here is using the GPT-4 model, and we've used some of the other ones but gotten, in my opinion, worse results. So that's why we were sort of stuck with GPT-4.
Thanks.
I see David.
Sorry if you already said it, but I was curious, did you do any measurements about energy efficiency this time, or is that future work?
I mean, that's a huge issue with AI technology and LLMs in particular. That's one of the reasons why I had hinted on this code generation approach, that instead of like, if we have to do something, let's say for every packet, then do you do that with the LLM, or do you have the LLM do a task once, which produces some code, for instance, that's going to do those tasks for every packet? And the energy efficiency is a huge problem, but also costs are prohibitive if you try to do some things a billion times with LLMs, for instance.
Very well, and looks like there are no more questions, so let's thank Jari. And this concludes a very long and fruitful day. I hope everybody enjoyed. Thank you to the speakers. Thank you to the TPC. Thank you to the audience. Thank you to the barista. Thank you to my co-chairs. Thank you to everybody. And I hope everybody has a good evening.
And thank you to you for organizing.